Welcome back, everybody. All right, in 10.1, we talked about a hypothesis test with two samples. Right, in 10.1, we had two samples, but either the standard deviation for our population was known, or, I'll say and or, our sample size was greater than or equal to 30. And what we found was that if it was greater than or equal to 30, we could use the standard deviation of our sample and still use a z-test. All right, in this section, we're going to talk about what if n is less than 30. All right, and our standard deviation is not known. All right, because if it's less than 30, we can't use the z-test. Our sample's just not big enough. Also, we're going to look at dependent samples. All right, so I first want to talk about what a dependent sample is. All right, so dependent samples. All right, so dependent samples are when subjects are paired or matched in some way. So there is some connection between the two samples. The most common dependent sample would be, for example, taking a class and doing a pre and post test. Right? If I took the same class and I gave them a test, then we did a treatment, and then I gave them the post test, that would be a dependent sample because the two samples would be connected by the same people. All right. Also, if a researcher wants to see how a drug affects a sample of users, right, he could do a pre and a post test for that drug. He can test, let's say, the reaction time of the sample before the drug and test the reaction time of the sample after the drug. All right. So academically, you could say a researcher would design an SAT course to help students raise their scores. So you would give a practice SAT before the course, and the students would have certain scores. Then you would give another SAT after the course. That would be kind of like your post test. And you would see what the difference in the scores were if there was what we call a statistically significant difference. So when the two samples are related, a la the dependent samples, all right, we can use what we call the paired t-test. All right, and there are some notation that we're going to need for the paired t-test. If I have my mu with little d as a subscript, that is the expected mean of the differences of the matched pairs. All right, so I'm going to pair some of this notation with our steps for success, because our steps for success, you're going to see, are largely going to be similar to the steps for success that we've had for all of our other hypothesis testing. There's just going to be a little extra to it because of the two samples. All right, so we're talking about one, we're talking about D, and that is x1 minus x2. All right, and basically what we're saying is we need to find the differences of the matched pairs. All right, after we find the differences of the matched pairs, right, number 2, so I need D bar. Now, D bar is going to be the average of those differences. So I'm going to sum up all the differences that I have, and I'm going to divide by the number in my sample, and that's going to get me the mean of the differences. All right. Then the next thing we need is I have S with a little d as a subscript, and that's for the standard deviation of the differences. All right. Again, it's the standard deviation of the differences. So we're going to do the square root of d squared minus the sum of all the d's squared divided by n, all divided by n minus 1. All right, and that's the standard deviation of the differences. All right. And then our fourth step, we're going to look for the standard error. Standard error of the differences, which is not going to be a big D. It's going to be an S, little d bar, is going to be our standard deviation that we found in step 3 divided by the square root of n. And that's pretty similar to what we had before with our standard error. All right, and then our fifth step is going to be to find our test value. And because our sample sizes are small, just like we did with our confidence intervals, we're going to look in our t distribution. So it's going to be a t. We're going to have d bar minus the mu of our differences divided by our standard deviation divided by the square root of our sample size. Again, very similar to what we had before. And our degrees of freedom are going to equal, once again, n minus 1, just like they did before. Our degrees of freedom don't always equal n minus 1 in every instance, so it definitely needs to be stated. All right, so I have one note on all 5 of these steps before we move on. And my note is that both populations must be normally distributed or approximately normally distributed. All right, and that's language within the problem. Sometimes you see that kind of language in the problem, and people get a little confused, but it kind of needs to be there, all right, in order for things to work out right. So without further ado, why don't we talk about a few examples? They are going to take a little bit of time to solve. Okay, a physical education director claims that by taking a special vitamin, a weightlifter can increase his own strength. 8 athletes are selected and given a test of strength using a standard bench press. After 2 weeks of regular training, supplemented with the vitamin, they are tested again. Test the effectiveness of the vitamin regimen at alpha equals 0.05. All right, right below I made a chart of the data that you need to solve the problem, and this data must be given. It was just easier to write it than to type it. So take a moment to write some stuff down, pause the video if you need to, and we'll get back to it in just a second. All right, hopefully you wrote down what you needed to, pause the video if you needed to, but we are going to get to it. All right, so the first step we're going to do in the overall process is going to be to state the hypotheses, right? And identify the claim. All right, so my null hypothesis is going to be that there is no difference, right? So that would be equals all right, so I'm going to say, just to keep all possibilities open, greater than or equal to 0, because my H1 is that the difference in my means is less than 0. All right, and that's the claim. Now, if we go back to the problem for just a second, right, we see it says the physical education director claims by taking special ed, it can increase his own strength. Yet my alternative hypothesis is that the difference in my means is less than 0. I'm going to make a better less than sign than that. There we go. And that's because if I take mu2 and I subtract mu1, and mu2 is greater than mu1, this should be less than 0. So the difference in my mean should be less than 0. All right, it's a little bit confusing. It was a little bit confusing for me when I was in your chair, but I hope you guys are okay with this. All right. So the next thing I want to do is I want to find my critical value, because we do need a critical value. All right. So for my critical value, I have my degrees of freedom, which is going to be n minus 1, or 8 minus 1, which is 7. And we need degrees of freedom for our t-chart. We also know it's a left-tailed test. A left-tailed test. And alpha equals 0.05. So why don't you pause the video right now, go to your chart, and let's see if you can get the right critical value. All right, so I got a critical value of negative 1.895. I hope you got the same. All right, so now for the test value, all the stuff we did up here is going to come into play. All right, we need all that stuff because our test value, we need our standard deviation, we need the average of our differences, and all that kind of stuff. So all right, so we have a lot of work to do before we can get a test value. All right, so I think the best way to be organized is to make a table. And x1 is our before, and x2 is our after. So I'm just going to copy down each of our weights. And you are welcome to do the same. This guy went down. It happens, but, you know, maybe he's having a bad day. 205, 204, he went down as well, not as much. And here we got a guy who went up a lot. 262, added 8 pounds to his bench press. That's pretty good. 253, 250. And lastly, 216, 216. All right. That's a terrible line down. I'm actually going to use my ruler. It's taking a long time. That's okay. There we go. That's better. Next thing I need is D. And D is x1 minus x2. So why don't you go through each column in your chart. I'm going to try to freehand this one. That was better. All right, and do the differences. So the first difference would be 210 minus 219 is -9. Then -6, then 3, then 1, -8, 3. Oh, I missed a piece of data. This is one of the things that could mess you up if you do miss a piece of data. So then I have 219, 222, which is -3. And 216, 216, which would be 0. All right, let's double count my data. 1, 2, 3, 4, 5, 6, 7, 8. I have all 8 because it said 8 in the problem. Next thing I need is my D squared. So I'm going to take my difference and I'm simply going to square it. So I get 81. 36, 9, 1, 64. Come on. 9, 9, and 0. Alrighty. So I'm going to try to keep my numbers up as long as possible. I need the sum of my D's. And so why don't you pause the video, add them up, and we'll see if our numbers match. All right, the sum of my D's looks like was -19. And the sum of my D squared, I gotta, come on, D squared equals, so why don't you add up your D squareds and let's see if our numbers match. All right, I got a number of 209. Now we're going to need both numbers because our next step is really what we need is we need our D bar, right, for our formula. So it's going to be the sum of our D's divided by our sample size. So take -19 divided by 8, and I get -2.375. All right. And so now we can go to my standard deviation of my differences. And to recall the formula, it's the sum of the d squared, which we got before, minus the sum of the d's and square them, divided by our sample size, divided by n minus 1. So let's put in some numbers, and I'll let you guys do the calculation. Square root of 209, which we already figured out, minus negative 19 squared over 8, divided by 8 minus 1, which is 7. I do like figuring out these numbers beforehand and simply substituting in, then trying to do them in my head on the fly. All right, so why don't you pause the video now and try to work this out to get the standard deviation of your differences. All right, so I got, hopefully you got the same, 4.84. Now we have all the elements we need for our test value, finally. All right, so I got t equals my d bar, which we figured out, minus my average of the differences, divided by the, make that a little more clear, standard deviation difference divided by the square root of my sample size. So for d bar, let's go back 1 second and see that we got d bar to be 2.375, negative 2.375. And the standard deviation of the average of our differences, let's go all the way back. So our null hypothesis is that they are equal, right? Potentially equal. So we can say that the average of our differences is going to be 0 divided by the standard deviation, which is 4.84 divided by the square root of 8. All right, so why don't you throw this into the calculator and let's see if we get the same number. All right, so I got negative 1.388. Hope you did too. And now we need to make a decision. All right. So when we make a decision, right, we can create a graph. I like creating the graph, as I've said on numerous occasions. And let's go back to our critical value. Our critical value was negative 1.875. 1.895. So that's going to be negative 1.895 over here. And if we fall in this region, that's the rejection zone. However, we fell back here at negative 1.388. So we make a decision to not reject our null hypothesis. And then again, we want to tie it into the context of the problem. There is not enough evidence to support the claim. And you guys can finish that up. All right, so there's example number 1. And take a look. All right, so now we're going to move on to example number 2. All right, next example. A dietitian wishes to see if a person's cholesterol will change if their diet is supplemented by a certain mineral. 6 subjects were pre-tested, then took the mineral supplement over a 6-week period. The results are shown. Can it be concluded that the cholesterol level has been changed at alpha equals 0.10. Assume the variable is normally distributed. All right, so I've given you the data. Take a moment to write it down. Pause the video if you need to. We certainly will need this data in just a moment. However, I'm going to scroll up because I need the space. And we're going to start by stating our hypotheses. And the first is that the average of our differences is going to be 0. And what that means to me is that there's no change in people's cholesterol, no significant change. And our alternative hypothesis is going to be that the average of our differences is not 0. And that means that there was a significant change. All right, that means the levels were different. All right. And if the dietitian wishes to see if a person's cholesterol will change, then I'm going to say that our claim is our alternative hypothesis. All right, so now we need to find our critical value. So that's step 1. Let's go to step 2. Our critical value all right, our degrees of freedom, we have 6 subjects. So our degrees of freedom equals 5. Alpha equals 0.10. And it's a two-tailed test. All right, so take a moment to find our critical value. Let's see if yours matches mine. Okay, my critical value that I got was plus and minus 2.015. And we're going to need this later. But now we got to compute our test value, right? And to compute our test value, we need a whole lot of components. We need, right? So for our test value, we need d bar. Hang on. We need the standard deviation of our differences. We also need sum of our differences squared and just the sum of our differences. So we got to make a chart, just like we did before. So I have x1 and x2. So then I have 210. I'm just rewriting the data at this point. 235, 170, 208, right? 208, 210, 190, 188. 172, 173, 244, and 228. All right, and my next column was to get my differences. All right, so 210 minus 190, 20. Then it's 65, negative 2, 2, negative 1, and 16. And then our d squared, we just take our difference and we square it. So 20 squared is 400. Glad you guys have a calculator to do 65 squared. All right, so then it's 4, 4, 1, and 256. All right, so we need the sum of our d's. So add them up real quick. Pause the video if you need to, but I got 100, and the sum of our, d squareds equals, I got 4,890. You're certainly welcome to check my work. All right, so now we have all the components to get our standard deviation of our differences. All right. So let's say we're going to use the same formula as before. So I'm just going to plug in some numbers. So I get 4,890 minus 100 squared divided by 6 divided by n minus 1, which would be 5. All right, so at this point, pause the video, run this through the calculator, and let's see if we come out with the same number. All right, I got 25 point, nope, that's a terrible 5. I'm gonna make a better one than that. 25.4. Oh, all right, so now we need our test value, right? After all that. So R equals all over the standard deviation divided by the square root of n. So if our sum of our d's was 100 and we divide it by 6, that means our d bar is 16.7. You're certainly welcome to check that. All right, and again, minus 0 divided by 25.4 divided by the square root of 6. So run that through the calculator, and let's see if our numbers match. All right, I got 1.610. All right, now we need to make a decision. So let's scroll up a little bit. And to make our decision, we've got to recall what our critical values were. So our critical values, 2.015 and negative 2.015. And our test value was 1.6. So our test value comes in over here. Remember, to the right and to the left are going to be the rejection zone. So our decision is we do not reject our null hypothesis, which means there is not enough evidence to support the claim and again, you finish the sentence, tie it back to where it was before. Okay, so one last example, and then I will let you go. And that is a way to use our confidence interval in order to make a decision on our hypothesis test. So if I said, find the 90% confidence interval right, for the data in the previous example. right, so we're going to use this formula, which is d bar minus T alpha divided by 2 times our standard error, which is going to be less than the mean of our differences, and then d bar plus T alpha divided by 2 times our standard error. All right, and again, a little bit less work, but I would only do it if you were directed to do this. All right, so we've did some of the work already. All right, so we're going to use some of that to our advantage. All right, so our critical value, we already got a critical value. Right from the last example, that was 2.015, which is going to, in this case, equal T alpha divided by 2. We already know what d bar is. That is 16.7. And we already know the standard deviation of our differences at 25.4. And we already know that n equals 6. Looks to me like we have everything to fill in the formula. So why don't you guys take a moment, pause the video, let's fill in the formula, and we'll see if we match. Okay, so let's take a look. So I got 16.7 d bar, right, which is minus 2.015 times 25.4 over the square root of 6. And 16.7 plus 2.015 times our standard error. All right, again, take a moment to work out the calculations and we'll see if our numbers match up. Okay, so I did my calculations and I wound up with a confidence interval saying negative 4.19 is less than the average of our differences, and 37.59 was greater. All right, so if we look in this confidence interval, what do we notice? We notice that 0 is contained in this confidence interval. All right, and if we go back to our null hypothesis was what? That the average of our differences was 0. So basically what this confidence interval is telling us is that we're 90% sure 0's in there. If we're 90% sure 0's in there, right, our decision is to not reject our null hypothesis, all right? So because 0 is contained in this confidence interval, right, we would make a decision not to reject because we're 90% sure 0's in there. We don't know if it's 0, but we're 90% sure 0 is in that range that it could have been. All right, again, confidence interval, we could be wrong, but 90% sure is pretty sure. Just like if we did our regular hypothesis test, we could be wrong. But again, you know, we only go based on the data that we're given. All right, there's many more examples to do. Like I said, they take a little bit extra. So I would definitely practice to cut down on your time. But thanks for listening, guys, and I'll see you next time.